So this is the first question on the statistics higher paper, paper 1, and we're looking at a Venn diagram. Shows information about 20 films shown in the UK. A is the event the film was produced in the UK, so there were 8 films that were produced in the UK. B is the event the film made more than 40 million, so there was 5 that made more than 40 million, and 10 that weren't made in the UK and didn't make 40 million. Explain fully what the number 3 represents in the Venn diagram. It represents the number of films made in the UK and made more than 40 million. One of these films is chosen at random. Find the probability that it is a film that is in B. Well, out of B, there are 5 in B out of the 20 films, so that will be 5 over 20. Next part says, find the probability that it is B given that it's already in A. So, there's 8 films that are already in A. The probability that one of those films is also in B is 3. So that's 3 out of 8. Now, part D says, using your answers to part B and C, explain whether or not A and B are independent events. Now, if they are independent events, then these will be the same fraction, the same probability. They're not. So 5 over 20 is not the same as 3 over 8. Therefore, they are not independent events. Question 2. There are 11,727 students at university. Their nationality is classified as UK, EU and international. The table shows information about the nationality of these students. The book manager of a bookshop wants to carry out a survey and books read by students at the university. She's going to take a sample of 600. She intends to sample 200 UK, 200 EU and 200 international. Write down the name of this method of sampling. This is a quota sample. She's got a set amount that she wants from each category. Part B. Give a reason why this method of sampling might not be appropriate. One reason, it's not representative. There's far more international students than there are EU, for example, and there's far more UK students. So actually, they should be asking more UK students than EU and international to make it representative of the population they've got at that university. It could also be biased because actually you've got a much better chance of being picked out of the 200 out of these 979 than you do out of these 9,393. So I'm going to go with this is not representative of the population. Okay. Shop assistant suggests it would be better to select a sample of 600 students stratified by nationality. Now, stratified sampling is when you look at the proportions that make it up, and we'll take the 600 down from there. Now, one way to do that would be to look at your 11,727 and think, what do I need to divide that by to get to 600 students, which you want in your sample? Well, actually, if you do 11,727 divided by 600, you'll find that that number is 19.545. We want to know how many EU students, so if I did 979 divided by 19.545, I would get 50.089. that means that I can have 50 students, if I round it, in that sample. Three students, Amy, Beth and Carlos, bought the same 8 books from the bookshop. The manager asked Amy, Beth and Carlos to rank these books in ascending order of how much they enjoyed them. The manager calculated Spearman's rank correlation coefficient for the ranks given by Amy and Beth. She got a result of 1.2. How do you know the result is not correct? We know that because Spearman's rank goes from -1, which would be perfectly negative correlation, to +1, which is perfectly positive correlation. 1.2 is bigger than +1, so I could say range for Spearman's rank is from -1 to +1. 1.2 is greater than this range. The manager also calculated the Spearman's rank correlation coefficient for the ranks given by Beth and Carlos. She got a result of 0.74. What does that mean? It means it's a positive correlation. Interpret the result. Right, so now we've got to think about, right, if it's a positive correlation, it means that they're agreeing with each other. What are they agreeing? They're generally agreeing that, that they're liking the same books. Okay, so we could say the students generally agreed on the books that they enjoyed. Maybe it would be better to say the students generally agreed which books they generally enjoyed. Question 3. We are finding the estimate of the mean distance jumped. You may use extra columns in the table. So we know there's one jumper that jumped between 7.1 and 7.3. So they jumped about 7.2. 7.3 to 7.5, 7.4. We're finding the midpoints for each one. 7.6, 7.8, 8.0 and 8.2. Now, as I said, we've got one jumper that jumped about 7.2, so I'll just write these numbers in here. 2 multiplied by 7.4, 14.8. 5 multiplied by 7.6, 38. 9 multiplied by 7.8, 70.2. 8 multiplied by 8, 64. 3 multiplied by 8.2, 24.6. Now this is the total distance, as it were, for each category. So these two jumpers both jumped about 7.4, so they jumped 14.8 in total. Now if I add all those numbers up, 7.2, add 14.8, add 38 plus 70.2 plus 64 plus 24.6, I should get a total of 218.8. Now that's my total divided by all my long jumpers. Well, these are all my long jumpers. 1, add 2, add 5, add 9, add 8, add 3. Add them all up, I get 28. So I'm going to do 218.8 divided by my total amount of long jumpers of 28. Should give me an answer of 7.814287. Now in the question it was all rounded to 1 decimal place, so I'm going to round mine to 1 decimal place and say 7.8 meters to 1 dp. Now we're going to draw a frequency polygon. Now a frequency polygon is probably the worst graph I've ever seen, but we'll do it anyway. It's asking for it. you look at the midpoints, you're plotting the midpoints and you're plotting them on the frequencies of those midpoints on this y-axis here. So I'm just going to write here frequency, and my highest frequency is 10. So just quick count, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. That'd work. So that's 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. First frequency, midpoint is 7.2, and that goes up to 1. Next one's 7.4, and that goes up to 2. 7.6, and that goes up to 5. 7.8, and that goes up to 9. 8, and that goes up to 8. 8.2, and that goes up to 3. Now, in our frequency polygon, we're going to join them up with a straight line between all the points. So, here we go. Straight line. Nice little dot to dot. Straight line. Straight line. Straight line. And finally, straight line. There we go. Describe any skew shown by the data where it's got a tail that's coming off down this side. So that means it's a negative skew. The majority of data is on this positive side here. So negative skew. So a nice pie chart question. We're looking at a pie chart of overseas visitors to the UK in January 2016 and July 2016. January, July. Key over this far side. Based on the two pie charts, Roll makes two conclusions. There are more visitors from Europe than from North America in both months. So if I look at those, Europe is this one, North America is this one, and we can see that the proportion here is bigger than North America. Proportion for Europe bigger than North America. So point number one is valid. The angle for Europe is greater than North America in both charts. Point number two, there are more visitors to Europe from Europe in January than in July. Now, the only way we know that is if we had the total frequencies or the frequencies of the pie charts. We don't have that information, so that is not valid. We only have the proportions, not the actual numbers. Judith decides to replace the pie charts with comparative pie charts. Explain how comparative pie charts are more appropriate than pie charts to compare the number of visitors in each month. Now, a comparative pie chart has different areas to represent the total number of frequency. So, whereas the pie charts are at the top of the page, you are just comparing proportions. Because comparative pie charts have different areas, we can compare the frequencies. So, comparative pie charts have an area that is linked to its frequency. Therefore, you can compare the frequencies. Maybe I should say its total frequency. Now it actually wants us to work out what the radius of Judith's comparative pie chart will be for July 2016. We've got the information of how many people were in overseas visitors to UK in January 2016 and July 2016. And comparative pie chart for January 2016 has a radius of 3. So we're going to start off with our radius of 3. So that's the one we're comparing it to. 3 multiplied by. Now the next thing we're going to do is find actually that sort of percentage difference between the two. I say percentage difference, we just need it as a decimal. So we start off with that new amount, 786,000, that's the one in July, divided by the original number, which is 2599000. And because it's an area, I'm actually going to square root that. Now if I throw all that in the calculator, 3 multiplied by the square root of 3786000 divided by 2599000. I get 3.66208, but to one decimal place would be 3.6 centimetres. So, the database contains information about 2,567 people registered at the medical centre. All the data information is date of registration, age, phone number, address, postcode, and number of appointments. Okay. She wants to see if there's a relationship between the age of a person registered at the medical centre, age, and the number of appointments this person has at the medical centre, number of appointments. Describe how Rebecca can plan to use technology to help her process and present the data for this investigation. You should refer to the advantages of using technology to process and present data compared to doing so by hand. Now the first thing I'm just going to check, 6 marks. Now it's asking me to do 2 things. So I'm going to put 3 marks here and 3 marks here. So 3 marks for planning, processing and presenting the data using technology. Well, when you say using technology, it means that we can sort or order the data columns really quickly using an Excel spreadsheet. If we wanted to pick random numbers, we can assign each row a number and then use a random number on Excel again, or a random number generator to pick out those appointments quickly. If we've got lots of data that we don't need, like we don't need the name, we don't need the date of registration, we don't need the address, postcode, phone number, we can delete that so we don't need it really. It's not interfering in anything we're doing. We can identify really quickly any missing information. So if someone didn't have their age in there, we can highlight that really quick just by doing a quick sort on Excel. If you had, let's say someone had put their age as 52 but they'd written it in words, that's really quick to change and to correct. We can use Excel to work out the mean or the sum or anything you want really quickly of a big data set. So we can get Excel, again, the computer, to calculate those averages or the quartiles or whatever you want really. We could also use Excel to make the graphs. So you could do a scatter graph, we could do, which in this case you would because you've got, you're comparing the age to the number of appointments. We want to see if there's a relationship. If we mention relationship, we're looking for a correlation. Therefore, scatter graph would be the best graph to go for in this case. And let's say we've got some outliers. So we might have someone who's been to 4 million appointments. We could take them out because that will affect our data. 3 of those points would get you 3 marks. Any of those points, so any 3. The next 3 marks are going to be for using the advantages of using technology. We've got it saves time, it can reduce errors in really long calculations, it can be easy to correct a mistake. We could actually, we don't need to do a sample, we could get Excel to work it out for all 2,567 people. Therefore, it's working as a census rather than a sample, and as we know, censuses are more accurate because it uses all the information. And if we make a mistake, it's quite easy to correct. Again, 3 marks for any of those 3 points. Question 6 is talking about runners. run it in a 5k race. Here are the results of some of the runners. Runner A, B, C, D, E, F, G. Nothing wrong with that. Maya wants to represent the results of all the runners using a stem and leaf diagram. Discuss two things Maya must do to the data to be able to represent it in a stem and leaf diagram. Well, the first thing she needs to do, when we look at this information, we can see here that it's not all in the same format. You've even got here, that's just a full stop, that's a colon, that's a comma, that's been written in, got words in there. So you need to clean it or format it to start with. So the data must be cleaned. Before use. The other thing we can do is make sure that we're using the same units all the time. Where it says 17.34, is that 0.34 of a minute, which isn't 34 seconds. 0.2 of a minute is not 2 seconds. So we need to make sure that it's in the right, using the right units all the time as well. So data must use the correct units. Finally, one more point. Before you do a stem leaf diagram, you would need to order the information. I'm not going to put that one down. I've already discussed two things. I've got 2 things there, 2 marks. But you could also have the data needs to be ordered. Explain whether or not it would be appropriate to represent the results of all the runners in the race using a scatter diagram. So a scatter diagram uses bivariate data, 2 lots of numbered data, the quantitative data. You haven't got 2 lots, you've got qualitative data and quantitative data. So not appropriate as not bivariate data. A histogram. A histogram uses continuous data. This is continuous data. So it is appropriate as it uses continuous data. And finally, a time series graph. Time series graph looks at something that's happened over time. Now, although it's saying race times, we'd be comparing back to like a race before or like last month, last year, so on. So again, not appropriate as the data is all taken from the same day. And there we go with question 6. Question 7. The table gives the simple index numbers with 2013 as a base year for the average prices of houses in Scotland and in Wales for the years 2014 to 2017. The table also gives the chain-based index numbers for the same information. Now, an index number is literally, it's like a percentage. How much has it changed? So a simple index number is using 2013 as the base, which means that in 2013 your answer would be 100 for 100%. Now in 2014 it's now 103.6, which means it's gone up from 100% to 103.6. How much has it increased? It's increased 3.6%. Again, simple index, it's always referring back to that 2013 as the base year. So in 2015, it's actually increased 10.1% from 2013. In 2016, it's increased 11.7% from 2013. The chain-based index actually compares year on year. So here, you see, from 2013, that was 100, it's gone up 3.6%. From year 2014 to 2015, it's gone up 6.3%. So from that year to that year. Remember, this one was going from 2013 up, 2013 up, 2013 up. That's just going from the previous year, the preceding year each time. So from 2015 to 2016, there was an increase of 1.5%. Give an interpretation of the symbol index number 103.6 for Scotland. We've already just mentioned that that represents a 3.6% increase. Represents a 3.6% increase in house prices from 2013 to 2014. David bought his house in Wales for $165,000 in 2013. Use an appropriate index number to calculate an estimate for the price of his house in 2017. So Wales, 2017, it's gone from 100% to 115%. So 115% is 1.15 as a multiplier. 165,000 multiplied by 1.15 will give you 165,000 times 1.15, 189,750. And there we go. Comment on the reliability of this estimate. Well, these index numbers are talking about average prices. Now, as we know, that's the average price for a whole country. That might not be very reliable estimate. Some houses will go up, or some will go down less. So we'll just say the index numbers represent the average house price increase. Individual house prices may have more variability. Right, by finding appropriate geometric means, compare and interpret the yearly average change in house prices from 2013 to 2017 in Scotland and in Wales. Now, geometric mean, in a normal mean, you add numbers up and you divide. In a geometric mean, you multiply the numbers, and instead of dividing, you find the root. So if you've got 4 numbers, which we have, we'll find the 4th root. So Scotland, I'm going to do 103.6 multiplied by 106.3 multiplied by 101.5 multiplied by 101.6, and the 4 through all of them. Now I find it using the chain base index numbers because that shows the increase each year, okay, from each year to each year. So that will give me an answer of, let's have a quick look, 4th root of 103.6 multiplied by 106.3 multiplied by 101.5 multiplied by 101.6, and that's come to 103.2 317,269. Going to do the same for Wales. 4th root of 103.0 multiplied by 103.6 multiplied by 102.8 multiplied by 104.8. 4th root 103 multiplied by 103.6 multiplied by 102.8 multiplied by 104.8. 103.5470771. So what does that tell me? Well, it says that the yearly rate of interest for Scotland is 103.2, which would come to 3.2%. Okay. And this one, 3.5%. So let's just write that down as a sentence because we've got to interpret them. The yearly increase in Scotland is 3.2%, whilst Wales is 3.5%. Now, just to make sure that we've got all the marks, I'm just going to make sure that we've compared them, which is greater, there we go, there's my comparison, than Scotland.